This is an exciting day because it is actually where I feel like two of the worlds that I've been playing in recently are colliding. I have Alex Milowski with me, and he is going to be talking to us today about geospatial sensor networks and partitioning data. And really, what I thought was the most interesting when we talked is this idea of how Kubernetes has changed the way that we think about what some might call data ops or data DevOps. And we're going to explore all of these topics and more. But before we do that, I'm sure you all see on your screen, hopefully, a picture of Alex and a bit of a bio on him. If you would like to know more, he's working at Redis Labs right now. He's doing some ML stuff. He's also had some past work at NASA, which is always a huge it just gives you a lot of credibility, Alex. I really think that's great. Now let's jump into it. Alex, can I start off by asking you how you got into tech and then how later on you started going into data science, ML, and all that?
Sure. Boy, how I got into tech. I'm one of those people that started programming when I was a little kid, and that was a long time ago. That was on an Apple IIe.
Oh, nice.
So I just started doing that when I was like 11, 12, and so and that time was a fascinating time to be working on computers because it was all new, at least. So and I've just stayed in it ever since. It's funny because I get my degrees are mostly in math, and my work experience has all been in computer science. So, and I've found navigated a sort of between the two.
Yeah, which
A lot.
super useful,
So,
especially doing data science and machine learning stuff that it seems like you've been diving into. Now, I know you have some slides prepared for us, but before you get into all of that, I just wanted to ask can we break it down, and maybe can you give us your best shot at explaining what is this data DevOps, or as some people
I
call
think
it,
the
data
challenge
ops?
here is, the there's the aspect of, you maybe have a system that's, pumping real-time data and you have a database, and that's great, but a lot of times people have data sets, that are sort of waiting in the wings, and the challenge, whether you're an enterprise or a researcher, is, how do I get the data set that I'm interested, the partition of it that I need, into some usable form, some database or some other, some other format that I can then process it, run my model on, do my analysis. And that aspect of manipulating data is, this is said all over the place in the industry too. This is where people spend all their time. And that's definitely been my experience over the years, and most recently with the scientific data sets. It's like the manipulation of the data just to get to the last piece, is the challenge. And we want to make that simpler and easier and more reliable so that we can do more ad hoc analysis and get to the real work that we're supposed to be doing. And that's the challenge. And I think that this is where I believe that Kubernetes has a lot to offer, because we have a language to describe the API is a language to describe the operations we would like to carry out, and then we have an infrastructure that can drive towards that successful completion.
And so a lot of times you hear in machine learning this idea of the data scientists spending the bulk of their time doing the cleaning of data, what you were saying, moving it around, or just trying to make sense of it. And you're thinking that Kubernetes has this potential in ways that I imagine you're going to get into in a minute, and how they're going to do that. But along those lines of the full potential of Kubernetes, when you look at it from the bottom of the stack to the top, like what are some things that for you get you excited?
Well, I think that for me, the recent focus on operators, I mean, I think the idea of a data operator is really interesting, and that because there's all this heavy lifting that, in when people who are sort of well staffed, they have these data engineers that can go and take the conceptual idea, from maybe a machine learning scientist and say, okay, now we need to scale this. Here's all the things we need to do to our data, and they know how to turn that into reliable code. So the idea that you could say what you want at a higher level, and an operator could go off and do those things for you in a reliable fashion is, I think, a very exciting idea. And that's that you do spend a lot of, the data engineering is a lot of the same kinds of things over and over again. And people who are successful at that, they build their own frameworks, so they have their own libraries, and they have their own policies, and so maybe we can encapsulate that somehow as an operator.
Awesome. Yeah, such good points. So I'll let you pull up the slides, and while you're getting all that ready and sharing your screen, I wanted to just take a moment and mention that these are excellent things that we've been talking about in the community, and some of those may be where a SRE role stops and a data engineer role begins, or what the benefits of operators are, what the downfalls could be. All of that is really great when you start digging into it. And I think that, like you said, operators have such interesting use cases and ways to use them.
All right. Are we ready?
Let's hit it.
All right. So here we are, Geospatial sensor networks and partitioning data. And just quickly, my outline here is just a bit about me. We've already talked about that a little bit, but I want that's one slide. And then we're going to talk a bit about partitioning sensor networks and what that means. And then how basically that work has evolved to Kubernetes, where I came from, with that kind of work, and then where we are now. And then I have a demo. So with air quality.
Awesome.
Timely here for California.
Yeah, very, very top of mind.
And so about me, I've been doing various things in technology and the web and RDFA and semantic, since around 1998. I've been heavily involved in W3C, and I did my PhD later in 2014, and that was basically on looking at the intersection of data, like scientific data and the web. How do we get data on the web so it's processable? And then I've been in and out of academia and industry in various ways, in startups, large and small, and taught at Berkeley and San Francisco State and a variety of topics. And so I've sort of been able to look at this from different perspectives. And more recently, my journey on Kubernetes, I was at Orange, and we were, about 2017, and I think Kubernetes sort of took the world by storm at that point. And we were looking at how do we use this technology to sort of support this data DevOps. When we have on-premise needs and hybrid cloud, and how do we move information around and for machine learning purposes. And we also had a question, sort of about data governance versus governance of data. And there's a distinction there, which is, subtle but important, which is, there's the legal aspects of, which is data governance, what laws do I have to comply with versus the policies that I want to apply to my data. And I was very particularly interested in how infrastructure can help, support and enforce and make policies for data operational.
Such a good point.
So that was some of the work I've been doing. And but to go back a little bit, we're talking about sensor networks here. And I was looking at data and different kinds of data sets that are, scientific data that people are producing. And I was looking for something that I thought was maybe not controversial, or something that was not not overly complicated, or would have privacy concerns, like or in industry privacy concerns. So like biological data is really interesting, but a lot of people keep that private. So weather turns out to be really interesting because there is this Citizens Weather Observation Program, CWOP, and it is basically a globally connected network of weather stations. So people run these they have them in their yards, their businesses have them, local government agencies have them, and it's so it's citizen science and citizen collected data. People, there were weather geeks out there. I became one of them. I put one of these up in my yard because I was interested in how it works. And there's this feed that you can get of an aggregated feed across the whole world, of all of these connected weather stations. And it uses this APRS protocol, which is it comes out of ham radio basically. So it was originally developed, for transmitting data over ham radio. And so it's got this kind of funky format and with station codes and so forth. But it's useful, and about 100 million weather reports come in per month, and that's that's 2014. So maybe there's more now, and there's about 800 different organizations that use this, including the NOAA here in the U.S. So our weather reports include some citizen collected data, and they clean this data. They go in and they see, is this a good weather report, and can we use this? Because there's more citizen weather stations than there are official government ones. Mm-hmm. So it was a very interesting feed, and it's geospatial. There's latitudes and longitudes. You kind of see it in that bottom piece as a snippet of the kind of data you receive. If you decode this whole thing, it's all coded in various ways and sometimes not correct. So that's the fun of collecting the data. Okay. And so the challenge here is to take this citizen CWAP data and create a measurement, a system for distributing this data, the cleaned version of it. And so part of my dissertation research was basically saying, how do we go about using this as an exemplar? And the idea was to, we take this weather data feed and we're going to receive it, and we're going to, sort of chunk it up into pieces, because we're going to have to process it over time. And we're going to partition it by the facets it has. So we have time and we have geospatial. And so times, we can think about that in sort of minute periods, but quadrangles is a standard map technique. They are basically rectangular-like areas, mapped onto a surface of a sphere, so they turn into triangles at the poles. And we want to turn this into something that's processable by web-enabled agents. So this was the idea. And so the challenge is to take this feed of 100 million web reports per month and turn it into these chunks of data, or data stored somewhere that can be turned into chunks of quadrangles and then encoded into a web enabled format. And I chose here for a semantic web enabled agent. So I was encoding this into basically web pages with RDFA data in it. And then that was the experiment to see, can we do something useful with that?
Wow.
So that's the challenge. And then again, this is circa 2014. So the whole infrastructure is running on VMs and databases, and I'm managing all these things in various manual ways. The part of the result of my work was this idea of saying, hey, there's a methodology here. We partition, annotate, and name. So we partition our data by regular facets, so time, geospatial location, and this enables algorithmic navigation. We have links between our partitions. We have annotations and names. We have ways, the partitions are reasonable sized so that we can retrieve them. And that means that we can create algorithms that can navigate our data based on the metadata that they have. They retrieve a partition. They have essential metadata that says, what is this partition? What's the data that you have? What are the links to things that are nearby and in some facet direction, maybe nearby in terms of a geospatial partition, a quadrangle that's next to you, or by time, going back and forwards in time. And this enables these agents to sort of move around in the data, and particularly algorithms to move around in the data. So in the picture, you can see there's a area of interest, and we can navigate that by looking at the different partitions. And these are labeled by what's called a sequence number. It's kind of like a geohash, but it's just a enumeration of the quadrangles in a standard way. And that way you can sort of compute. You can compute from one sequence number to another, things that are nearby, and you can also navigate by time partitions. And this worked out really well. One of the things you want to do, right, is produce models like weather maps, right? Like I want to take the temperature readings, and I want to produce a sort of gradient surface there, color coded of what the temperature is in all places. So this is actually something that I think the interesting part of computer science here, but the Stanley Barnes came up with this atmospheric interpolation model, and it was a discrete algorithm. It was a dynamical programming based, and it was able to be done in a very small amount of memory on an IBM mainframe in 1964. So this is great fodder for things that can now run easily in the browser, because it's we have a lot of computation power sitting right there. And but what you can do is it basically, you can think about this as saying the interpolation process is, I have a region of interest. From that I can retrieve the data. I can compute this sort of grid average of the discrete values that the sparse readings that I have from the weather stations wherever they are, and then I want to interpolate the whole set of atmospheric temperature for the whole grid. And so this is kind of like a MapReduce process. So part of the work that I did there was actually doing this in the browser. This is an example.
Oh wow.
We had this extreme weather event in North America in January of 2014, where this is the polar vortex. It came, this is very cold weather, came very far south in the US. So this was computed in real time in the browser, accessing these data partitions using this sort of MapReduce process written in JavaScript, and it took about 22 seconds to generate this interpolation grid. And over half of that was the data access, which is not a surprise. So this is 2014 browsers. They're probably a lot faster now if we were to do this today, but the data access is what it is. And so I think that's that was an interesting result from my work there. But the sort of getting there, right, is the challenge. And so I think the interesting thing here is dissertation research are the kinds of things where at some point you stop and you write your dissertation. So I had to put this down. Maybe I could have re-architected this in different ways and made it better and based on my knowledge, but I put it down and I moved on, and I did some other work I think that's interesting. But I wanted to talk a little bit about the challenges here. And I think that, this is the dev, circa 2014. The challenges here are, I had to keep this whole system running. The polar vortex happened, while I was working on writing my dissertation, and it just happened, since I had a system running, I was able to capture that sort of event and then to produce that picture that I just showed. But keeping it running was a challenge, right? Because here I have, a bunch of VMs running a bunch of different things, and, collection, I have this reliability problem where the servers on these APRS IS services that I'm connecting to, they changed. Literally, the server names changed at different points in times, and things would go down, and their end would go down, and my end would go down, and so I had this reliability problem, which was a challenge. And I had to come up with clever algorithms for retrying things, and then literally I just had to check in on it every so often. The simplest, maybe crude method was I was dumping things to partitioned data files on disk. I would run out of disk space, simple things like that. I had the same challenges with my database. I was running a MarkLogic database. I had the infrastructure sizing there. Every so often I would run out of space. I had a certain amount of infrastructure could only hold a certain amount of data. So I had to trim data from the database just because I'm not running a production system for, the government. I'm for my research. And same thing with ingest. What do I ingest? How well does that go? If I need to reload my database, how long was that going to take? The reliability of that service. What do I do when things go wrong? These are all things that Kubernetes can address. Item potency is a system property, but it's a good thing to have. Where I can run the import twice and I won't get duplicates. Basically is a simple way to think about that, and that's a good thing because it makes the data DevOps easier. So those were a lot of the challenges I faced. But it's kind of looking at a slightly different system here. This was a NASA challenge project, and they have this OpenNEX as a climate model, and it's stored in this HDF5 format, and these massive files that are sort of a file, like it's used for like satellite images and so forth. So there's a library that you can get, a C library that can process these. And so it's this kind of funky often a corner data format that's used a lot, but you have to have special software to process it. And so the challenge here, I thought, was, well, we want to put this on the web. We want to make it accessible. And so at the time I was teaching data engineering course at Berkeley, and I thought this is a great example of on-demand Amazon, EMR, for Hadoop, basically to do this kind of data processing. And again, you can use this as infrastructure. And so the big picture on the right is basically processing these HF5 formats from S3 and via map tasks into data partitions, and restoring them back into S3, and then getting the data out of this funky format, doing some averaging, doing some stuff, producing these partitions, and then making a web application that can read these partitions in different ways. Here it's all static. The model doesn't change. There's no new sensors, but it is geospatial data. And we for what we did, here we got a little award from NASA, which was great. But I think the interesting part here is again, it's we go from handcrafted scripts to Hadoop as infrastructure, and it worked out reasonably well. But I think we can do more. And so that's where we get to. So the evolution, now that we have Kubernetes, that was still 2014. What would we do differently, right? So I feel like I've been on this collision course with Kubernetes in various ways. I've been building distributed computation systems and for math and other things like that over the years. And so here I am doing this data collection and ingest and analysis work in various forms. And this is, the three different parts of this have characteristics that I think that, if you're doing collection, you want to have this reliability of the data source, and you have long-running jobs, and you need to deal with outages. And one of the things about sensor networks is it's ephemeral data. Once the data is transmitted, if there's nobody to receive it, it's done, it's gone, right? So downtime means gaps in coverage, and especially for things like CWAP, it's a real-time network. It's meant to move that data fast, and it really is gone, right, if nobody's receiving it. Ingest is kind of a similar thing, where you have this challenge of going from raw formats to some kind of cleaned observations. Some systems just want basic syntactic validation. Others, like the National Weather Service, is interested in. So you measure temperature in your home weather system. There's a model for whether that's a valid observation, right? The air temperature can only increase a certain amount in a certain amount of time, and things like that. And they run these models to check that is that a good reading. And then there's some issues about the question of like near real time, like how fast do they want to get these things. And then analysis is the same kind of challenge of like you have batch and ad hoc and real time analysis issues here. So we want to take that data and ingest it in different ways. And then we have the applications also of computational models, like the interpolation that I was doing in the browser. That's fun to do real time, but if you're doing that as say a weather service, you're probably going to run a model, and generate a set of predictions that's going to be reused. So that's more of like a batch type of.
This is fascinating.
Yeah. So I think on the data collection side, I think this is not controversial. It's not, not amazingly, not a grand revelation here that there's a clear win in Kubernetes, right? We have long-running processes for data collection. Right? We can parallelize them with Kubernetes. We can deal with restarting after failures. I think the operator paradigm gives us a great path for evolution here. So you go from basically scripts and programs running in a VM with all the typical upkeep problems to pods that are collecting data that can be scaled out, where we can store the configuration and the authentication, credentials and so forth, and secrets. We can manage all that complexity with the principle, the sort of fundamental building blocks in Kubernetes. So I think that's a clear win from a collection standpoint. Just just the complexity of just the configuration parameters and things would, just to begin with. Not even talking about scale out. But like in the case of CWAP, I think there was like 5 different servers I had to connect to. So basically, I had to run 5 different collection, pod based processes, right? So that's 5 different pods on Kubernetes that I have to run and keep running. So I think that kind of thing of being able to say, I have one of these things, slightly different connection parameters, but it's the same kind of thing. And now we have a language for saying that. We can describe that job or that pod, that deployment in a common way, and parameterize it. So that's great. And we still have this challenge of like the raw data. I mean, sensor networks, again, you have this, you're collecting ephemeral data. And I think the guiding principle here is, from a data science standpoint, is you want to capture as much of that raw data as possible, right? Because any interpretation that you apply is an interpretation, and maybe you're wrong. Maybe your algorithm is wrong. So you really just want to take the raw data and put it somewhere. So in the old world, I was basically running these scripts, and I was storing them in files, and maybe I could have done better and stored them in object storage. And I think the collecting pods, they're doing a very similar task. And the only difference is, we're probably not using local storage. We are using object storage. We're going to have a better reliability, but it's kind of the same model of, we're collecting data from the source and we're pushing it somewhere as fast as we can, as reliably as we can. This is not real time, right? This is just, capturing what is out there. But we can think about what it means to go real time, and I think this is where you still need
All right.
to record, for reprocessing the data that you're receiving. So you still need to push it to object storage, but you can think about a streaming queue where you push data on there. You're probably still partitioning it. You're not going to put in an individual observation because they're so tiny, but you're probably going to chunk them in small periods of time, and then you're going to have some kind of a queue and then some kind of a reader for that queue. It's a great thing to be able to reuse that ingestion pod, because the data is probably the same. How it gets its data may be slightly different. And I think the thing to realize about geospatial data in this context is it is like real time. It's still not really real time, and we're not taking each observation and processing it as we receive it as fast as possible. Maybe we don't need that, and unlikely we don't need that. If it's air quality, a 10-minute window, is more than sufficient. And if it's air temperature, again, you may be looking at this as like the current air temperature, as being reported to some consumer. So again, you may want to run processes that average that over a certain time period. So you're looking at a partition of time for the use case, and then how can I serve that data within that partition of time? So I think it's a little different. Depends on your use case and whether you really need real time, because that's a hard thing to do. So I have a demo, and PurpleAir is a provider of sensors. So you can buy these things and you can put them in your yard, and a lot of people do. Turns out, I didn't know that, but now it's been incredibly useful because, again, a lot of people, they've checked PurpleAir's website, and I discovered that in fact they have an API, and they very kindly produce through the API. As long as you don't overdo it, you can take that data and you can get a bunch of air quality readings for wherever they collect it from. So I built a little example of this thing where I'm basically collecting air quality data. I started this about on the 25th of August, and so the architecture is real simple. I'm a single resilient collector that's running talking to PurpleAir and trying to be nice to their API and collecting the data on a 5-minute partition. And then basically storing it in 30-minute chunks into object storage. I have an ingestion process that can take that data from object storage and push it into Redis. And Redis is, from a perspective of the application, it's just Redis. So OSS Redis. But I'm actually using an operator the Redis Enterprise operator to deploy a cluster so that Redis database, that surface, is in fact running in a cluster. So I'm using an operator to manage that. And then I have a single, like a simple Flask-based application that can do interpolation, which is also running inside the cluster. So this is all based on Kubernetes. So the infrastructure here. And the nice thing about this is, again, like that configuration management has just been so nice. So that's the thing. And I'm going to show this here in a moment. So I collected data from the greater Bay Area, and I didn't want to collect a huge, massive amount. So I've only been, it's a big quadrangle area, it covers most of the sort of greater area here. I've been collecting since the 25th, and I discovered, that's about the time that I discovered that there was an API. The way it's stored in, there's a standard OSS Redis feature for geospatial data sets. And I think it's interesting that basically I have a key partition in the Redis. And the way this works is that the key value has a sensor and an offset into the partition. So, 10 minutes in, 12 minutes in for this particular sensor ID. And then the set of observations. And the way that that works in Redis is basically, it's kind of a reverse model. The key is the value, and the score in the set is the geoposition. And so that gives me the idempotency, which I desire. And then I have a simple interpolation model. It's not an air quality model. It's not something that EPA or somebody would use. There's a lot more that goes into that. Did a little research on that, and then I realized that's a lot of work. So it's just simple interpolation. So let me pull that up here. I'm going to stop sharing this, and I'm going to go to demo. Yes. So let's share that. All right. And I assume you guys can see all this. So we're looking at a particular interpolation here, and it's what you see in the top here is just the data that I've loaded in, and I can select different partitions here, so I can go back, and this is today actually. So this is what the air quality looks like. I can change that, earlier today and roughly right now. It's gotten better, right? Somewhere on San Mateo, what have you. And we can. So this is hitting the loaded data that's in Redis, and we can sequence this. So this will show you. I have actually. So if you pick the 9th of September, that's the day that San Francisco turned orange and the sun didn't come out. So we can run that. And this is, again, is an example of just, this is real time pulling from the database, running the interpolation, and then serving the interpolation. So interpolation is being done in the Flask app, not in the browser. The browser is just creating the visualization. And so this is a Kubernetes, this is not really necessarily Kubernetes, but the whole infrastructure is running there, which is nice. And, this was actually really straightforward to do. I think the combination of being able to sort of slice and dice this in various ways and be able to describe that in Kubernetes terms, let me do this very fast. And then, this will continue going, and I can change the size of things and make it less 8-bit looking, but you can see it gets pretty bad at different points in time.
Yeah.
There's.
I have just a quick non-Kubernetes question, but for the data collection out in the ocean, how does that work? Because I imagine there's not people out there.
Right. So this is the thing about having just an interpolation that's just based on math. This is not an air quality model that is taking into account that, wind and geography, right? So you would probably have a model that would discount, although the smoke is going out into the ocean, but there's probably different ways in which that is dealt with in terms of how smoke dissipates or particles dissipate in marine air versus over land, and all those kinds of things. This doesn't do that. This is just a mathematical algorithm that says, I have a grid, I have these values, I can interpolate them in different ways and using various forms of linear interpolation. So that's why I say this is not an air quality model. It does give you a rough approximation, but I think you have to discount some things where, like over water, for example. But there are actually, in a place like the Bay Area, there's a lot of these sensors. So it's probably more accurate in places where there's a lot of sensors versus places where there's less. But anyway.
Wow.
So there's, take the picture you're seeing with a grain of salt. I'm not the EPA.
Yeah.
Or the National Weather Service.
But it's fascinating how you were able to do that. And the first question that comes to my mind is, how much of this that you've done now on this new architecture with Kubernetes do you feel is because Kubernetes makes it easier? And how much is it just because you've already done it once and you feel like, all right, I know how to do this, so I have the heavy lifting is done?
Yeah, I mean, I think I have one more slide. I think that can address some of that.
Okay.
So let me go back to the slides here. I think, oops, you got the slides? Yeah, here we go.
Yeah.
All right. So go back to presentation. I think the thing about it is, in the last couple of days, as I basically preparing for this talk, I have been tearing down and standing up the infrastructure in various ways. I have the collection job running and it's just doing its job, and it has been running relatively flawlessly for a while, which is great. I don't have to worry about that. But now I have this challenge of like, I'm playing with different things and looking at different characteristics of how can I speed up interpolation. Let's make sure I have the right data in there. I tore down my Redis database, I put it back up, and different things. So what I eventually did was this thing I'm showing you here, where I wrote a little Python program that takes a templatized Kubernetes job and lets me adjust the parameters, right? So I go in there, I can tell it, the time periods that I'm interested in, and I can configure the data source and the target, and I can like there's a 6 or 7 particle measurements. Which particle measurement am I going to use? So here I'm using the 10-minute index one is the 10-minute measurement, and so that job I can basically create a fresh database, configure the secret for the database access, and then just run these ingest jobs by generating them via this little program and applying them and so forth. So I can basically populate a new database really quickly. And the sort of most raw speed I've been able to achieve, I can load a day of data in like 70 to 100 seconds. So I've been able to sort of stand up and tear down infrastructure. I think that's a huge difference for me from the past, where that was a monumental task, right? Because it just wasn't that easy to describe. I don't have the building blocks, and I think this is where you can imagine that within certain parameters for certain kinds of data, at least, that an operator could be really useful, right? Because then you can say instead of saying it in these terms with the sort of Python program that sort of knows something about the structure of my job, you can say it in terms of what the outcome that you want. I would like to have this many days of data in this database, and sort of say it by name, and then the configuration of the operator and the other things in the custom resources knows how to get the data and where to put it, and the credentials are there somewhere, and you, the user of the data, have just described what you want. And that also plays well into organizations where they want to separate concerns from the consumers of the data and the users of the data in terms of who has the credentials to do it versus who has the ability to say what they want, right? And that's, and RBAC can be used in there as well. And there's all kinds of potential for being able to deal with the governance of data, which is, this is where come back to that
first slide. When you're talking about the
governance of data
differences.
is a huge deal. It's not just that. It's not just organizations that have to deal with GDPR. They have to deal with governance of data. It's also about, like, privacy concerns and infrastructure concerns. This all costs money, right, to run this infrastructure. So maybe you're an organization that says, it's great that you want to do these model building tasks, but we want to make sure that we do this in a cost efficient way, or that you're not just asking for, ridiculous amounts of data, which ends up scaling our cluster to ridiculous sizes and ends up costing us lots of money. There's a way to manage that over time. And this is, what people have done with centralized Hadoop infrastructure. This was at, Orange, we had a massive, sort of internal Hadoop cluster, which queues and permissions and different things you could do. And that's how they sort of managed access to compute. And I think you have the same kind of challenges on Kubernetes that could be solved in various ways, in useful ways as well.
Yeah, that's fascinating.
That's my last slide. So
that's awesome. I really appreciate you going through that with us and showing us the evolution of the air quality that you've built in 2014, and then how you've managed to recreate it here. And it's like you said, it's a perfect time for you to create that and let us see. I mean, the pictures of this, the Bay Area, are incredible. We've all seen pictures on our phones from friends, or those of you that are out there that better than anybody, but seeing it also in this map and watching it change over time is really a great just visual idea of what's happening. So let's jump back into a few questions that I have on the role of databases. And I know you're using Redis. Do you feel like there should be more and databases that should be thrown in? And then the storage aspect, you talked about how in the beginning of when you were working on this in 2014, you were just using up all of this storage. I imagine now you didn't have that problem because you weren't just using up all of the disk. So can you talk to that a little bit?
Sure. I mean, the challenge, I think one of the challenges for this kind of work is, and I'd be curious to talk to the PurpleAir data. I haven't done that yet. For example, just in terms of, like, you'll have this sensor network and it's producing all this data continuously. How much do you keep, right? And for what purposes? And so there's a historical aspect to that. But there's also a question of, like, the cold and colder storage, right? You can keep pushing that sort of archive to colder and storage, and that's great. But your live data, is for some purpose, right? So it's either the current reporting, or to support model training, for predictions for the future, or to support, say, climate research for a certain period of time. And so that partition of time that you need and the geospatial region that you're interested in is very particular to the work that you're doing. And that ability to sort of slice off the raw data, put it somewhere, and in a usable form, that's the challenge, I think, for databases, is this question of, like, I need to stand up infrastructure, that can support the creation of this database and with the properties that I want. And then I need to ingest that data in a reasonable amount of time so that I can then do some work. And I think there are different use cases there where, the real-time monitoring is one thing, but the researcher or model builder, or, person who has some task to do, they have this requirement of saying, I need this piece of data, I need it to have these query capabilities, I need to shove it into that database, and the faster it gets there, the happier I am. And then there's the balancing out of that, in terms of, like, how much does that cost, right? And am I cost conscious or not is a big question. Because you could also, there are things you can do more like the way, say, Hadoop works, where there's just data files, and you're processing those data files over time to produce some interpolation or something like that, or train some model. And then you're accessing your data maybe many times versus being able to query it. There's challenges in all these things. The databases make the world simpler because in the case of this particular data set, I put it into a geospatial index, which means that, I query it based on geospatial properties. So I don't have to think too hard about, in the ingest process, it's just put it in the database. And then the consumption process, it's like, I'm going to make the geospatial query that I want, right? So I can choose the size of the geospatial partition based on that query. And then those things are separable and the concerns are separate. In a batch processing model where you don't have a database, then you have to think about those things. So those are hard concerns, and they're interwoven in how your processing code works. So I think that's the one of the challenges I think for database vendors is making that. And this is where operators I think are really important for databases, is making that ability to say, okay, I want a database. It needs to have this kind of size characteristic and these kind of performance characteristics, and the credentials are now generated for me or available to me somehow, and now I can use those to ingest my data and do my processing. And maybe when I'm done, I'm done with that database, and it goes away. Or maybe it's there for some long period of time or longer period of time, and that kind of ad hoc versus temporal infrastructure, I think, is also another interesting aspect of where databases need to go. This idea of a long-lived database is great, but it's also like, I might just stand that up for, ad hoc purposes where ad hoc might be days, but it's not, it's not forever.
It makes me think about like Mission Impossible, and this will self-destruct after
Right.
5 days or 10 days, however many you give it a lifespan, and you say, after these 2 weeks, I don't need it anymore. So just go ahead and let it blow up. So the other question that I had on this, speaking of challenges, like let's dive in a bit on the challenges. You mentioned it a little when you were talking on the slides, but the challenges for these sensor networks, and how do you address these challenges within the Kubernetes environment?
Well, I think the one of the main challenges is one of the two main challenges. One of which is just the ephemeral nature of sensor data. So if your infrastructure goes down, if your collection infrastructure goes down, you're just going to have a gap in your data, and that can be true, on the other side of the fence. Whatever aggregation system you have is the same story. If the APRS system goes down, you don't have citizen weather data. If PurpleAir's data, collection system goes down, we don't have PurpleAir data. So that's, that across the board, that kind of reliability of the collection process is a challenge. And it's one thing like I have gaps. The way I'm collecting my data is fine for now because it restarts things and restarts quickly. But there are gaps in there because when things fail, and I've run into some data issues from the API, and I've run into code issues in my own thing. And, there's a bug and the thing fails and then it starts up again, and I'm like, well, what? I have to sort that thing out, and I lost some small segment of data there. It's just gone. And fortunately, I'm collecting things on a 30-minute time period, so it's not a big deal, but it might be for other things. And that aspect of like just a pod restart doesn't really quite cut it. And so if you want to build, if it really is sort of mission critical to always collect this data, you need another form of resiliency. You need some checks and balances there. Maybe you need to collect the same data from multiple collectors. Hope not everyone has the same problem. And you need a way to understand what was happening at the time and see if you can recover from it. So in the case of pod restarts, you might have, overlapping data, and you now know that you need to sort of merge something somewhere. And you want to record that event. And that's where I say that, like, I think an operator for collection and ingest and things like that could be very interesting, because it would have a higher level view than just pod restarts, right? Like, it's great that you restarted the pod, but then what do we do differently with the data because of that? Or even just to record the fact that there was an outage and it was this long, and so that people know that there's a gap in the data and we shouldn't rely on that.
Oh, yeah, that's a great insight. That's super useful, right? If you're looking at it and you don't have to go back through and say, what's happening here? Why am I not getting this?
One of the metadata things that when you go and get data sets, you can go data.gov and get data sets that are published for various things. And one of the things you get for geospatial data especially is what you think of as an extent, like what region of the world does this cover and what time period and other facets, right? So computing extent of data, is an important aspect of what your process is doing as you're collecting the data. So time downtime is, changes the extent of the time period, right? And there's gaps in there. And then same thing goes for, like, maybe, if you're collecting data from different servers that serve different parts of the world, then you might have geospatial outages for time periods, so you have to think harder about how that data how that's recorded. And the challenge there is, those can be hard problems to solve from a sort of computer science standpoint. Like, what is the right algorithm that has the right kind of recovery and failure and metadata recording is not necessarily an easy thing. And so, things that can reduce that burden, whether they're libraries or operators or whatever, are really going to be good things for this kind of work. And I think that's where, if you're going to follow the sort of Kubernetes mindset, I think this is again where I keep going back to operators, but again, I think that's kind of idea of, like, taking it up a level and letting those hard problems be solved once, maybe, if it's possible, and and then at least or at least maybe give people building blocks that are more reliable, that they don't have to try and solve all those hard problems over and over again. Would be an interesting evolution for sort of data DevOps.
Incredible to talk with you, Alex. I really appreciate you showing us what you've been doing and taking the time to give us this presentation and really enlighten me on all that you've been able to do. And I think it is a super interesting point of view that you're coming from, and you're opening our minds, showing us some things that could be better, showing us some things that you definitely advanced on over the years. I really can't thank you enough for coming, talking to us. I want to let everyone else know that is here. If you want to continue talking to Alex, what's the best way to continue the conversation?
Oh, I'm on the Slack for the community, right? So we can start there. That's always a good.
There we go. Good
I'm always
answer.
open to conversations. It's I think people's particular problems are always fascinating to me. I like talking to people about their challenges and sharing knowledge. So that's
yeah, it's obvious you have a lot of knowledge to share. So I really appreciate you coming here, taking the time, talking with us. I will finish with that. We'll leave it. We'll be back here next week, same time, same place. See you all. Thanks for staying with us.